Hello, my name is Edgardo Cheb-Terrab, and I would like to talk about the functionality available in the Maple system for doing algebraic computations in physics. So, first of all, why computers? Physicists do their algebraic computations with paper and pencil, and they are very successful in doing so. So why would we use computer algebra in the first place? Well, I think that there are several advantages in user computers for algebraic computations. So first of all, you can concentrate more on the ideas instead of all the details of the algebraic manipulations. You can extend your results in easy ways. You can change the values of parameters. You can add equations to your system. You can change the form of the potential in your problems, and so on. You can explore the mathematics around your problem in very easy ways. For example, you can plot, you can compute series, you can check for special values for some special functions that maybe enter your problem. And not less important, you can share your results with your colleagues in a way that the results are reproducible, because you can send a worksheet and your colleagues can reproduce all your computations and even change part of these computations and send the worksheet back to you. And in this way, you can exchange about a problem in a very productive way. So if it is so good, why is that computer algebra were not being used by physicists more? And the reason, I think, is that there was a severe representation problem with regards to the mathematical objects typically entering in physics computations. So, for example, if you go to the Wikipedia and search for Maxwell equations, you will find this table. In this table, you see abstract notation for coordinate-free representations for vectors, coordinate-free representation for the Nabla differential operator as an upside-down triangle. You see the square representing the D'Alembertian already working in relativity theory. So this is tensor notation. They are contravariant, covariant indices. Maybe the space-time is curved, so the covariant, the non-covariant derivative becomes the covariant derivative, and this covariant derivative includes Christoffel symbols. This represents the square root of the determinant of the metric, and so on. And the computer algebra systems were not designed to compute with this kind of abstract notation with so dense mathematical contents behind. The situation is not different with regards to quantum mechanics, where the standard notation is direct notation. We compute with Ketz and Brass, representing, for instance, in an infinite dimensional case, representing these integrals. The product of a Bra and a Ket represents this integral from minus infinity to infinity. The mean value of an operator, where all these operators are non-commutative with respect to multiplication, in the case of a discrete basis, represents this sum, and so on. And we want to compute with the objects you see on the left-hand sides, but with them representing the contents you see on the right-hand sides. And again, computer algebra systems were not designed for this kind of notation originally. This situation is changing. We have implemented most of these things in the computer algebra worksheet in the Maple system. And so I want to illustrate a little bit both the abstract notation that is now available for algebraic computations in physics and some of the problems that can be tackled with this notation. So I choose 5 examples, 1 in classical mechanics, 2 in quantum mechanics, and 2 in relativity. Where my intention is not to go into the details about the physics, but just to illustrate the algebraic computations and the power of this more abstract and compact notation used in physics. So my first problem is to determine the inertia tensor of a triatomic molecule that has the form of an isosceles triangle with two masses in the extremes of the base and a different mass in the third vertex. The distance between the two masses M1 is equal to A, and the height of the triangle is equal to H. The context for this problem, well, this is a textbook problem taken from the Landau book for mechanics. So for the solution, we start with the general formula for the inertia tensor, and we already see these new objects where we see a vector. This is an algebraic vector, not a matrix. Is a coordinate-free representation for a vector. Is the norm. This is the Kronecker delta symbol, and these are the components in the I and j directions of the kth vector, where k goes from 1 to n is the number of particles of the system, and m are the masses. These vectors are the position of the particles as seen from the center of masses. Okay, our problem has 3 particles. We create an indexing function to represent the inertia tensor as a matrix using this compact Maple notation, where we construct a matrix just using an indexing function. On the diagonal, we see the standard formulas for the components of the inertia tensor. Out of the diagonal, we see also the standard formulas related to each of the 3 directions, and so on. So in our problem, 2 masses are equal, and now we want to move away from the position vectors as seen from the center of mass to the position vectors as seen from an arbitrary system of reference. So the formula is that the position of each mass as seen from the center of mass is equal to the position of this mass as seen in an arbitrary system minus the position of the center of mass. So we choose the origin of this arbitrary system to be at the middle of the segment connecting the 2 atoms of equal mass. So the first atom is to the left, a distance A divided on 2. The second atom, same mass, is to the right. Again, the distance is A divided on 2. And the third atom is over the third vertex of the triangle at a distance H, is the height of the triangle. So the formula for the center of mass is this one. This is all standard. And because now all these vectors are defined, we can compute a value for the center of mass. So this is the position of the center of mass as seen from the arbitrarily chosen system of reference. We put the origin at the middle of the segment connecting the 2 atoms. So now we can compute these little vectors, which represent the position of each of the 3 atoms as seen from the center of mass, because these are the objects that enter the definition of the inertia tensor. So all the objects are defined, and therefore the little r1, r2, and r3 are given by this. And now all the objects are assigned, so we can directly compute the value of the inertia tensor by simply evaluating the matrix. So summarizing, we start with a very abstract formula for the inertia tensor, components of non-projected algebraic representations of coordinate-free vectors, coordinate-free representations. Then we have a matrix of somewhat abstract formulas, do few assignments, and we get the value. This illustrates well the kind of computations that can now be done with abstract vectors. Okay, going to something different. The first problem in quantum mechanics, I want to check that if 2 so-called conjugate variables satisfy a relation like this, that is, the commutator is equal to some constant, then the deviation with respect to the mean values of these conjugate variables, the product of the square of these mean deviations, has a lower bound, which is equal to h squared divided on 4. To show this, we start introducing Q and P as Hermitian operators, and the algebra rule that governs the problem, that is that the commutator of Q and P is equal to this. And then we introduce a basis of kets psi. We will label it by psi, and we will say that these kets are normalized to 1. And with this, we can already introduce the mean values of the operators Q and P as the brackets. And now we can introduce the deviations from these mean values. For that, we introduce another Hermitian operator, delta, which by definition, delta is equal to the deviation with respect to the mean value of the operator, in this case Q, in this case P. And interesting, because of the algebra rule already set, which is this, the deviations from the mean values automatically satisfy the same commutation rule. So the commutation for the objects on the left is equal to the commutation of the objects on the right. The commutator of the objects on the right is computed and is equal to this, and therefore we have another commutator relationship. We add this to the algebra rules in order to take this algebra rule at the time of simplifying. To find this lower bound for the product of the deviations with respect to the mean values, we define a kets psi that involves the application of these deviations, delta q and delta p, over an arbitrary any ket of the basis, and we introduce a parameter lambda. We will soon see the why. This parameter is real, and we now take the square of the norm of this ket, and we obtain this relationship. Now, here we see that there is the mean value of the product of delta q, delta p, and here is the mean value of the product of delta p, delta q. Of course, these objects don't commute, but their commutator is equal to the imaginary unit times the Planck's constant. So we can factor out the mean values and collect these two terms and apply the algebra rule. This is what the simplifier does, simplify with respect to the algebra rules, and obtain this relation. This is a polynomial of second degree in lambda, so its discriminant is negative or 0. So we compute the discriminant and we isolate h squared and immediately get the lower bound for the product of the deviations with respect to the mean values. Again, a rather abstract computation. It can now be performed in a natural way. Our second problem in quantum mechanics is the derivation of the field equations for a quantum system of identical particles. The background for this is that quantum systems of identical particles, if they are of boson kind, they enter a number of relevant problems nowadays, typically in the form of Bose-Einstein condensates. I will not go into details. In this moment, I'm just interested in computing the field equations for such a system. Okay, these equations are computed by constructing the Lagrangian and then minimizing the action by equating to 0 its functional derivative with respect to the field. So the first step is to introduce the energy density for a quantum system of identical particles. According to standard formulas, is given by this expression, where we see the norm of the gradient of C, we see the absolute value of C, V is an external potential, and this term is the atom-atom interaction. Between bars, we see the absolute value of the C field. We indicate the real objects of our problem, and now we construct the Lagrangian in terms of the energy using standard formulas again. So for this problem results in this Lagrangian, where we see the conjugate times the time derivative of C and the conjugate of that product, and so on. And now it's time to construct the action. The Lagrangian is just the integrand in a four-dimensional integral. And this is the functional derivative we want to take. So we want to variate psi in form and apply this variation to this functional and get the terms up to first order. Here we are delaying the evaluation of the operation using quotes. And now we just perform the computation. And this is the result. It comes very rapidly. It's a complex operation to be done with paper and pencil. And it's essentially already the field equation for the problem, but for the fact that it's not entirely simplified. Here we see three terms that can be collected together into the Laplacian, actually the conjugate of the Laplacian. So we introduce an inner form for this Laplacian, and now we substitute these three terms in the conjugate of that expression to obtain this, and now we just isolate the time derivative is here. So get this, and applying just some collection, we get the gross Pitayevsky equation in its standard form. Again, a simple computation nowadays on a computer algebra system, on a computer algebra worksheet, but a rather abstract if compared with the things that could be done a few years ago. And now I want to go into two examples from relativity to make more complete the presentation. So the first example is to derive Maxwell equations in the tensorial form, departing from the four-dimensional action for electrodynamics. So for this, we first set a coordinate system. We define the four-dimensional electromagnetic potential. It's a tensor, A mu. With it, we define the electromagnetic field tensor that enters the action for the problem. We define it the usual way as the antisymmetric combination of derivatives of the potential. And now we want to equate the zero, the functional derivative, where the integral in the action is actually the contracted form of the electromagnetic field tensor. So it's F mu nu squared. Again, we want to vary in form the potential A rho, and which means each of the tensorial components. There are these derivatives, the mu and the nu, and well, we want to perform the operation, and here it is. So this is the tensorial form of Maxwell equations, but for the fact that they are not really simplified. We see contracted indices. Here is mu, and here is nu and nu, here is nu and nu here. There is a D'Alembertian here, and there is a D'Alembertian here. So we want to simplify this expression with respect to the contracted indices, taking into account Einstein's sum for repeated indices. The simplifier of the physics package is this one, and here we are now with Maxwell equations in tensorial form. All nice, but where are the differential equations? Well, this is a tensorial expression, so let's compute the tensor components of this equation and convert the D'Alembertian, which is a second-order differential operator, to the standard diff Maple form, and here are Maxwell equations in standard Maple notation. To conclude, I want to talk about a problem in general relativity. It's a bit more complicated problem. This problem was presented to me a month ago by a Maple user who wanted to know how could he do this kind of computation on a computer algebra worksheet. So in his problem, the space-time metric is given by this expression. So it's a curved space, there is curvature, and he wants to compute the trace of this tensorial object where phi is some function of the radial coordinate, non-specified. R is the Ricci tensor. These, the alpha and the beta, are the covariant derivatives, so each of them has an extra term involving the Christoffel symbols. And this is the stress energy tensor given in his problem by this matrix. In second place, he wants to compute the traceless part of this expression. And in the third place, he wants to compute an exact solution to the nonlinear system of differential equations conformed by the components of the traceless part of Z. First of all, the trace of Z. Well, we set the coordinates. He worked in spherical coordinates. We introduced the line element for the space-time metric, the way he indicated. With the line element, we just set the metric, and we can just check that the metric, the covariant components are as he indicated, and indeed it is. They are. So now we introduce the energy tensor, the stress energy tensor. We define this to be a tensor so that we can compute with the components of this thing. And now we solve item A in one go. Just define a tensorial equation. We will call this Z. And define this so that we can compute with Z representing this so abstract tensorial equation where each object in turn is defined in terms of other tensors and other tensors. For instance, the Christoffel symbols are defined in terms of the space-time metric and so on. So to compute the trace, then we just write it is the contracted form of Z, and we zoom over the repeated indices, and there we are with a differential equation representing the trace of Z. Here, VRR, for instance, is the second derivative with respect to R. If you want to see this in the standard Maple notation, we just make it happen. Now we want the components of double, the traceless part. Okay, this can also be solved in one step. By definition, the traceless part of Z is Z minus the trace of Z multiplied by the space-time metric divided the trace of the metric. So we define now double to be that tensorial equation in terms of tensors that are defined in terms of tensors that are defined in terms of tensors and so on. And then if we want the components of double, we just get all the components at once. It's very interesting how abstract is this computation and how rapidly it proceeds nowadays. Again, we have that the components form a system of differential equations, and in fact, this user asks for an exact solution for this system. So we first construct the system with the non-zero components of double. We run a differential elimination process in order to see how many cases are behind. And indeed, there are three cases. So one is the general case, two are the singular cases. Two cases are singular. The first two cases involve rather large expressions, but the third one is small enough and can be tackled to the end. We see that the first equation is just a constraint between lambda and phi. Then there is one differential equation that is easy, one second differential equation which is second order nonlinear and coupled with phi, and then a simple first order linear equation for phi. So we first split into the constraint and the subsystem. We solve the differential equations. They happen to be solved in exact form. And now we use the constraint to connect one of the three constants that appear here. In fact, if we evaluate the constraint at this solution just computed, we see that there is a relation between C2 and C1. We solve for C1, and we substitute this into the solution just computed, and in that way, we get the solution to our original problem, or the system, which is the system conformed with the components of double, which in turn is the traceless part of this expression for Z. We want to verify that this result is correct, and indeed, this solution cancels all the system. And that's it. Thank you for attending this presentation. I hope you enjoyed it.